Principles of Operating Systems, Chapter 1. The computer system consists of several hardware components, processors, memories, system buses, storage devices, input devices, output devices, and software. Lots of software. All of the software can be considered as being either operating system software or application software. The operating system is particularly important. It has several functions, including controlling the access to the processors, provides a set of services to users of the system, and controls how they interact with the system, and it manages the system hardware components. Now, the early computers were big and expensive. As time passed, they started getting even bigger and more complicated and much more expensive. But then in the 1960s, there was a change. The computer market divided. The personal computers, mini computers, less complex, less expensive, became available. Dividing the market like this didn't, in fact, make a big change in the development of operating systems until about 10 years later in the 1970s, when the microprocessor was developed. With the microprocessor, it became possible for computer companies to design and market personal computers, selling computers to individuals rather than institutions. Before the introduction of the personal computer, all computer systems were operated by specialists, computer operators. But, of course, personal computers being sold to individuals generally don't have the finances to contract their own system operators. So the development of the personal computers required a user interface for users. The simplicity and ease of use of a user interface became much higher priority in designing operating systems. Of course, systems that are easier to use, so user-friendly systems, can be marketed to a much wider audience. There are a lot more individuals than there are institutions and user system operators. Now, the earliest of the personal computing systems had very limited resources, and so the operating systems had relatively simple things to deal with. They did not have very much RAM, and they didn't have very sophisticated external storages. They had slow processors. The earliest of the personal computing operating systems tended to feature menu-driven interfaces, interfaces that were simple to implement and didn't require very many resources. Systems that were easy for the inexperienced users to understand and to use. Later on, as the personal computers became bigger and faster, they and their external storage systems and their user displays became bigger and faster. More complex interface systems were developed that made personal computers even easier for untrained people to use. Now, people have been working regularly to make their computers do more, to work faster. One of the things that they did was to try to create multiprocessing systems that would deal with more than one process simultaneously. They even designed single chips with multiple processors built in. A chip with multiple processors built into it is called a core. A multi-core processor, then, is a single chip, a single computing component that has two or more independent processors, processing units, each of which can read and execute program instructions. Processors. Clearly, the idea behind this development was that several processors working at the same time should be able to do more computation than just one processor functioning. Of course, this requires some part of the system be able to identify which process can be processed together with which others, which sequence of processes are inherently sequential. That is, one has to be finished before the next one starts. Now, multiprocessor systems certainly have advantages over single processor systems. The main one is, of course, that with several processors working at the same time, several kinds of programs anyway can be finished faster than with just a single processor working. And there's also a factor that if one of these processors fails, there are others that can continue executing, continue processing. Although, of course, the system won't be work quite as fast, it will keep going. Now, the multiprocessor systems are much more complicated. The operating system now has to keep track of which processes can be assigned to which processors, which processes can be executed simultaneously, and, as we'll see, they have to be capable of identifying and avoiding deadlock situations. Of more complex operating systems require more memory and require more time spent executing operating system code rather than the application code. So, if our problem is inherently sequential, the multiprocessor system might even end up being slower than a single processor system, assuming, of course, that the single processor is as fast as any of the multiple processors available in the multiprocessor system. With the arrival of the smartphone, combining telephone and computer in one unit, there came the necessity of designing different kinds of user interfaces. Since a smartphone has a smaller display than most computers, and most of the users of the smartphones won't have any formal training and will have relatively limited experience in the use of computers. And of course, there is the necessity for the computer portion to interface with the telephone portion. There are lots and lots more smartphones than there are general purpose computers. So the operating system on smartphones are vastly outnumber the operating systems on standard computing systems. In fact, there are even more embedded computers than there are smartphones. So embedded operating systems are even more numerous than are smartphone operating systems. Computing system hardware has become quite cheap, and it's commonly built into lots of other products where you might not expect them. Basic household appliances, automobiles, pacemakers. Embedded systems can range from digital watches, MP3 players, all through huge routers and switches. Embedded systems are generally designed for specific functions, and so their operating systems are quite different from those that you'll find in a general purpose computer, and definitely different one from another depending on the function. The complexities of these commercially embedded systems can range all the way from single chips all the way up through huge multiple processing chips with RAM built in. Now, the key feature for an embedded system is that it's designed for a specific function. But in order to get them to perform that specific function, very often they require general purpose processors to deal with the kind of functions in different ways depending on the application. When we have an embedded system, typically these are going to be limited in the available RAM and ROM, and the operating system has to be tailored to the specific requirements of this system. In order to get the optimum efficiency in terms of speed and size, it's not uncommon for the software developers to write all or much of the code for the embedded system directly in assembly language. This gives you the users or the developer the best possible speed and size, but at the cost of portability and maintainability. When they can, the developers prefer to write their code in higher level languages like C. One big difference between many embedded systems and desktop systems is that the embedded system will be running one single statically linked executable image. Standard computing systems typically load and execute different applications, whereas your embedded system has one application always in RAM in the system executing. So you don't load applications. There is an application loaded at all times. When we have an embedded system, typically these are going to be limited in the available RAM and ROM, and the operating system has to be tailored to the specific requirements of this system. In order to get the optimum efficiency in terms of speed and size, it's not uncommon for the software developers to write all or much of the code for the embedded system directly in assembly language. This gives you, the user or the developer, the best possible speed and size, but at the cost of portability and maintainability. When they can, the developers prefer to write their code in higher level languages like C. One big difference between many embedded systems and desktop systems is that the embedded system will be running one single statically linked executable image. Standard computing systems typically load and execute different applications, whereas your embedded system has one application always in RAM in the system executing. So you don't load applications. There is an application loaded at all times. Communications have come to be a major factor in use of computers. And so operating systems have had to deal with computer communication and networking. The term network operating system can be used to describe two different kinds of things. It could refer to a specialized operating system for things like routers and switches, or can refer to an operating system that supports networking. This kind of such operating system supports sharing things like files and printers among the multiple computers in a network. These kinds of operating systems enable the data to be shared, supports user groups, provides support for security and multiple networking functions. Just about all of the modern operating systems have come to include these kind of features. They're just expected anymore. The early microcomputer operating systems, CP/M, Apple DOS, MS-DOS, Mac OS, were designed for use of one user on one computer, no communication among computers. But as the technology improved and became more common, it became necessary for operating systems to use and deal with this technology. They evolved two distinct approaches to the kind of sharing done by networks: peer-to-peer networking, client-server networks. In a peer-to-peer network, the users can share resources and files on their own computers with the other users, and they can access the shared resources of other users. They don't have centralized management sources, and all of the connected computers have essentially the same ability to share and access resources on the network. The advantages of peer-to-peer systems: they're relatively easy to set up. They don't require special hardware to implement, and they don't have a central server that requires special hardware or software. All users are essentially equal. Their disadvantages: they don't have a central location, so the storage is limited to what is available on the individual user systems. And having no central server or central management, they don't provide the same level of security that does the client-server model. When a network is based on the client-server model, the server provides resources that can be shared by multiple clients. The client-server operating systems centralize the functions and applications in servers. And in such a system, the server is a center of the system. It provides the clients access to its centralized resources. This way, the server can also provide security by denying access to users who don't have proper authorizations. These network operating systems then provide mechanisms for integrating components of the network. It allows multiple users to share the same resources simultaneously, independently of their physical locations. The client-server model then has several advantages. It has greater stability because the centralized servers, generally more expensive, will have professional staff maintaining them. keeping them up to date. They have greater security because a central server can check authorizations of the users attempting to access their resources. They have greater flexibility because it's easier to integrate and update new technology and hardware and software, again, due to professional staff and maintenance. They generally will have better performance because, again, the hardware will tend to be more up to date and will be specialized with a focus on the performance. The remote access will generally allow access for users having different kinds of systems. Of course, nothing is perfect in this world, and the client-server model would have some disadvantages. One is that they will be more expensive. The server requires greater capacity, will be more expensive, and the professional staff doesn't come cheap. They all depend on a central location for their operations, and this provides one possibility for the system to simply go down. If the server goes down, the system goes down. And, of course, regular maintenance and regular updates are necessary because of greater dependence on the central system, and that requires extra expense and time.